Okay, for area questions, it's very helpful if you can draw the graph, except that since you have x equals to y squared, some of you might have trouble thinking about that. So let's try to figure out the graph of this first, and then we'll move on to actually solving the problem. So first, think about x equals to y squared. We want this graph because we have the concept of a parent function, right? So you have this function and you're moving this in some direction to get that one. It's actually 4 steps left, but we'll talk about that afterwards. Let's first figure out what this is. Well, this graph is just like y equals to x squared if you switch x and y, right? If you switch x and y, these two are exactly like the other. And this one everyone knows how to graph, right? And then you have to think about what this operation is. What happens if you go from here to there? X is replaced by y and y is replaced by x. And the following picture is helpful. Here's x, here's y, here's like negative x and here's negative y. And if x becomes y and y becomes x, that's like a rotation, right? Can you tell me where is the axis of rotation here? If you do this, where's the center of the rotation? You're rotating with respect to what? Huh?
1, 1. Like with the center.
Okay, vector 1, 1. Okay, so vector 1, 1 would be the center of rotation. Usually people call this y equals to x, the diagonal. If you have y equals to x, that's the diagonal line. And if you rotate around that diagonal, that has the effect of swapping x and y. X becomes y and y becomes x, right? So what it does is that, see, this is opening in the y direction, right? Guess what's going to happen if you swap this way? The resulting graph will be opening in which direction? X direction, right? Positive x direction. So you're going to get a parabola that's like that. Okay. So that's the graph, because when you rotate, this becomes this becomes that, right? So when originally it was opening in the y direction, now it becomes opening in the x direction. So that's the graph of x equals to y squared. And you can even try plugging in a few values to verify that it is indeed that graph. Like plug in y equals to 0, gives you x equals 0, so it does pass through the origin, right? And then if you plug in y equals to 1, then x equals to 1 as well, 1, 1. If you plug in negative 1, you get positive 1, so it's negative 1, positive 1. Positive 1, negative 1, and so on and so on. You can plug in a few points to verify that indeed this is the graph that satisfies the equation. Now once you have that done, the next task is to figure out what this graph would be. This graph is like you're subtracting 4. So the value of x will be decreased by 4 every time, right? So if you plug in 0, you get negative 4 as the x value. So what's happening? Your coordinate that you're on will be negative 4, 0. You're going to have a point here. Okay? When you plug in 1, it will be 1 minus 4, so it will be negative 3, 1. So you have negative 3 here and positive 1 here. And then when you plug in negative 1, again, it will be negative 3 for the x coordinate, and y is negative 1. So once you get these 3 points, and knowing that this graph is some kind of a shifting of this in some direction, you can kind of see that, oh, this must be 4 steps left. So this must be the graph. Okay, so once you have the graph of the first one, then let's try to put the two graphs together. Let's also do this. If you plug in x equal to 0, you get y squared minus 4. And that's true when y is plus or minus 2, right? So you have positive 2 and negative 2 as your y-intercepts. Here's negative 4. And you have a parabola passing through those points. Okay, what about this one? Y goes to x minus 2. What is that? That's a straight line, right? It's like this. So it's going to meet somewhere. And therefore, where is the enclosed area? Right here. This is the enclosed. Okay, so once you have the graph done, then now we can figure out the area. Now, to find the area, you basically have two options, either top minus bottom or right minus left. And it all depends on how you dissect the area into small pieces, right? So the way we calculate is always area is sum of its pieces. But this is ambiguous. What do I mean by dA? That's something that you have to choose. Okay? Which way are you going to cut it into fine pieces? dA means a very, very small piece. And there are two options for us. We could do split this way. In such a case, the length will be top minus bottom, but it's extremely hard to get, well, it's not extremely hard, but it's hard to get this side and this side subtracted. And in the middle of the integration, the top and bottom the bottom equation changes, right? It follows this curve and then suddenly changes to that one. So although it's not totally impossible, it's not easy to calculate that way. Okay. The better method would be to cut this not in that direction, but to cut it this way. Now if you cut it that way, then it's always right minus left, and the right equation is this straight line that doesn't change, right? The left one is this parabola, that doesn't change. So you only have to handle just one integral as opposed to two. That's why you want to choose this way. Is that okay?
You should write it in terms.
Hmm?
Don't you have to write it in terms of y?
That comes later. Okay. The question was, don't you have to write it in terms of y? That comes later. Okay. Right now, I really want you to look at the picture and decide whether it's easier to cut it this way or this way. The rationale I was giving is that if you cut it this way, then the equation has a transition. First it was following this curve, but then it follows that curve. You cut it this way.
Would it be easier to cut it horizontally? Because the line it's a steeper line. It would be easier to cut from the horizontal.
No, it doesn't have anything to do with the slope of the line. It just means that if you use horizontal lines in this picture, the right side is following a single function. On the left side is also following a single function. It doesn't transition in between. You see what I'm saying?
Yes.
Yeah. So by easy, I mean ease of calculation. It's easier to do just a single integral than two integrals, right? Don't you think? Yeah. Here, I can't represent, if I cut it this way, I can't represent it as a single integral. I have to write it in terms of two integrals. One going from here to there, because top, bottom, right? And from here to there, it's a different equation. So you end up having to do two integrals. It's harder. Is that fine? Okay. All right, so let's now try to write an integral in that direction. We're doing this. So I'll just name the curves. Let's call this name as C1 and this one as C2. This curve will be called C2 and this will be called C1. And in order to get this length, I have to do this minus that to get this length, right? If you do right minus left, then you get the distance between the two. Subtraction gives you distance between the two. And you want to do right minus left because if you do left minus right, then you get a negative value, which is not what you want. You want to do right minus left. So that gives you C2 minus C1. But then that's just a straight line. It's not, it doesn't have an area. To make it an area, we need to thicken it. Which way do we need to thicken this?
In the y direction.
In the y direction. See, we make this is very, very thin, but we thicken it ever so slightly in the y direction, so we multiply by dy. Okay, we multiply by dy. And then, the next thing you realize is that since I have dy, the bounds and the function must be in terms of y. Is that good? There's a logical flow there you have to understand. See, it looks like I'm not doing anything that's really hard here. It's like, oh, anybody can write this. That's true for any quantity that's physical. Area, volume, mass, you name it. It's always like this, right? So I'm just writing it like this. That's like a principle of how you apply integrals to find anything. But then here to there, I'm just looking at the picture and I decide to chop it off this horizontal way. I'm describing it as, oh, to do it this way, I must be doing right minus left, and I should be thickening in the dy. But the moment you decide to put the dy here, it has implications. What are the implications? Can you repeat what I said? Repeat what I said? If I put dy, what are the implications of that?
It's in the range of y.
The range must be y. The bounds must be y. Y values, right? What else?
We're increasing it over.
C2 and C1 must be functions of y. Those are the two implications. Okay? It's simple. You just have to keep track of what's needed. It's like cooking. If I want a sour tasting stuff, what do? We need a vinegar. Just think about what we need, and then you can figure out the ingredients. All right. So that means I need to know the y coordinates of these two intersections. So what should we do? We set them equal to each other to find the intersections. So let's find the intersections. What do we set equal to? Now, first of all, if you just say y squared minus 4 equals to x minus 2, that doesn't work because it's not an equation of single variable.
Don't you plug that in?
Yeah, that will be one thing. So it's really solving a system of equations, right? You're looking for x and y, pair of numbers x and y that satisfy both equations. So since you already have it solved for x, you just plug this into the other one, and that's how you solve it. So you have y equals to y squared minus 4 minus 2. And then subtract y both sides, and you get 0 equals to y squared minus y minus 6, because negative 4 minus 2 is negative 6. Oh, I know how to factor this. This is y minus 2, actually y minus 3, y plus 2. So that you have y equals to, what is it? Y equals to 3, and y equals to negative 2. And I already know that they meet here. This is 0 comma negative 2, right? And if I want to know this value, well, y value is 3, that we know. How do you get the x value? Just plug into one of them. So if I plug in 3 squared is 9, 9 minus 4 is 5. So I know that this coordinate is 5 comma 3. I just figured out the x coordinates just to get a better idea, but that wasn't really necessary. All we need to know was what goes here and there. What goes here and here?
Just 3 to get to.
Negative 2.
Negative 2 until
Right.
3. It's from the smaller number to the bigger number, right? So you start from negative 2 and goes up until 3. Okay. Now, the next thing to do is we need the curve C2 and C1 to be described as functions of y. In this case, it's okay. This is already described as a function of y, right? Okay, C1 is described, this is our C1, that's C2. This is already described as a function of y. X equals the function of y. But this is not. What should we do?
Big two.
Add to both sides. If I take this and add to both sides, then I have x as a function of y. Right? And this is what we need to put for C2. Okay? So C2 would be from -2 to 3. C2 would be y plus 2 minus, you have y plus 2, y squared minus 4. Right? So I have C2 minus C1, so this minus that. That's what I have. Okay. Now we just integrate. This is integral of -2 to 3 of negative y squared plus y plus 6 dy, which is -1/3 y cubed plus 1/2 y squared plus 6y, and then you have to plug in 3 and -2. This is -9 plus 9/2 plus 18 minus positive 8/3 plus 2 minus 12. So that's 27/2 minus -10, -30, -22/3. So let's see, over 6, what's that? 3 times 7 is, that's 81. Plus, why is it 44? So you get 125/6. Right? Okay, so that's the question.